Do you want me to give you any cues during your presentation, like breathing cues? To give you any cues during your presentation, like breathing cues?
Yes, definitely not this. Everyone sounds horrible on.
Yeah.
You sounded like a little baby.
Thank you.
How do we check the stream now? Let's see on my phone.
I mean, you just did, right?
Yeah, I want to see how the white looks. Okay, let's do a tricky one.
What is a tricky one?
Because that needs sound. So we have to mute its microphone. Because that needs sound.
Because of Zoom? But why? Yeah, this wouldn't like produce any sound anyways.
Yeah.
Yeah, this wouldn't like produce any sound anyways.
Okay, good. Good. Yeah, after I like this.
What? You said you want to. Do you want to like kill the lights or keep them?
If we kill the lights, then the video is too. Maybe my video is
I need like a video.
yeah, it looks okay.
Video doesn't seem to be.
Okay, now let us send this link to everyone in the world.
What?
My mama must have woken up early to watch it, so.
Probably for the critique. But I'm impressed with the style.
Yeah, I think I'm going to make it like a uniform. Like seriously, it is. I've been thinking about it, like blue jeans and
Shirts.
yeah,
Yeah,
I love them.
It's a good uniform. But that seems like an expensive shirt.
It's a nice shirt.
Yeah, right. It's like a nice
It's
shirt.
not that expensive actually. Maybe like $80.
Yeah, but it's a nice shirt. Yeah.
I mean, it has been very useful. Like these $80, like went a long way.
Yeah.
Like at least 4 or 5
But
jobs.
it's honestly, it looks brand new. It doesn't look like it's been used, like,
Yeah,
especially since it's white.
I also learned how to take care of shirts.
Okay. Yeah, because like you would expect white shirts to like fade.
Yeah, so you have to like
afterwards.
bleach them, iron them properly, and other such shit. So I googled and learned all this. Who else do we put to? Who are you?
Us?
What?
What are you saying?
Who else do I send it to?
Just post it on your Facebook.
Yeah, that I don't want to do.
Why?
I don't know.
I think it might even be against like PCA regulation.
switch on the audio.
Okay. So Ameet is connected. Is like the audio. He's like this. All right. So we're gonna get started. So shall we close this door? Okay, here we have a world-famous Pratik, who's going to entertain us for the next 35 minutes. It's great that he's here, and I've learned a lot from him during the past few years. So I have people in the audience. So here's the conclusion of his PhD journey. Please.
Thank you for a very kind introduction. Good afternoon, everyone. Welcome to my thesis defense. I will talk about the training process of deep neural networks today. Let's. So let's begin. First, I would like to tell you a little bit about myself. I am interested in building autonomous systems. These are robots that live in the physical world with us, among us, and that can interact intelligently with this physical world. And when I say intelligence, what do I mean by intelligence? Let me show you this video. So I took this from the movie on AlphaGo on Netflix, and this is just before the 4th match with AlphaGo. And it is already up 3-0 in this game. And these commentators are kind of trying to wonder as to what a human being, the best one in Go at that, might do to defeat such an amazing machine. And you see, like, one of them says so very easily, so very nonchalantly, like, if you want to defeat AlphaGo, just pull the plug. It is as simple as that to kill a computer program. And this is the essence of intelligence to me. Intelligence really serves survival. Such an intelligence is the ability to control the environment around you, to affect events that happen to you in the future. Of course, this requires perception, the ability to predict what is going to happen to you in the future. Intelligence is kind of the glue that sits in between perception and control to create an agent of this sort. And these are the kind of robots I would like to build. Things that are intelligent, not just in the sense of an AlphaGo or a chess playing program, but they're also intelligent in the sense of a job. Well, how far along are we in building these things? Before coming to UCLA, I did my master's at MIT, where I worked on problems from stochastic estimation and control, POMDPs, temporal motion planning using temporal logic, so on and so forth. A lot of this work was focused towards autonomous driving, and it began in roughly 2012-2013 as a mobility on demand vehicle in the campus of National University of Singapore. It kind of became large scale in this MIT spin-off called Neutronomy, where we began to build full-size autonomous cars that could go around the city, do a lot more interesting tasks. But we should ask ourselves, like, have we really solved perception? Have we really solved autonomy? Not really. So foolproof perception today is still a very, very hard problem. If you have sensors that can sense very far away from you, but they don't understand what is going on in the real world. If you put me on a road with 15 cars around me, it's very difficult to understand what these cars are going to do in the next instant. You can always be very reactive when you form plans in the physical world, but you are wasting a lot of effort while doing so. And that is when I was kind of getting attracted towards deep learning around 2014. Deep networks are a very good way of assimilating large amounts of data at very low latencies and then coming up with clever answers. Perception, which was before, let's say, 2012, it is still a very hard problem, but before 2012, it seemed kind of out of reach, suddenly seemed a little more plausible if you put deep networks into the mix. How well does a deep network work today for the purposes of autonomous driving? Well, it depends. So if you are building a photo album at Google or Facebook, you make a 1% error in your predictions, no harm done, right? So people move on. In the real world, however, the standards are much, much higher. If you take today's state-of-the-art object classifier and put it on an autonomous car right away, it doesn't quite work. And this is what we call as the mysteriousness of deep networks, or the dark art of building systems that have deep networks in them. Deep learning works today. That is beyond debate. How to make it work? How well does it work? These are the questions that we are asking. And these are the questions that my thesis focuses on. The goal of my thesis is to kind of capture this art into the basic principles of deep learning, unravel these mysteries using mathematics. We cannot limit ourselves to just this, though. We want to come up with algorithms that push the envelope of practice. The practice in deep learning today is decidedly very far ahead of what we know about them, but that is what we would like to push for. The remainder of the talk will be structured as follows. So first, I will give you a qualitative picture of the energy landscape of a deep network from the view of optimization. In the second part of the talk, I'll talk about how to aid first-order algorithms while traveling on this landscape. So these will be smoothing methods. The third part of the talk finds some properties of stochastic gradient descent, which might be completely surprising to us, people who use stochastic gradient descent, and which might give you a lot of insight about what is going on in machine learning and optimization. A deep network today, for the purposes of this talk, is a very simple object. It is a nested application of affine transformations on your input data. So you feed an image from the left, you apply these transformations, these are interleaved with nonlinearities, which is how they get their true power. And out comes a probability vector, which classifies your input image as a cat, a dog, a car, or a boat. One of the biggest problems in deep learning today is how do you go about training a deep network? Why can we even train them in the first place? How do you go about making sure that the network that you're trained on a training data set works well on a new data also, or it generalizes? You can write this down very abstractly as an optimization problem. So X are the parameters of your neural network. X are the weights. You're trying to find the best set of weights, X star, which is the argmin of a function f of X, which is the loss function. It measures the mispredictions of your model with respect to some ground truth data. And you would like to minimize this mispredictions. You want to capture a lot of variability in your data sets. We have very rich data. And so you want X to be a very large object. Deep networks today have tens of millions of weights. It is a high dimensional optimization problem. We are also feeding them data that is equally rich. It is a large scale optimization problem. One of the key bottlenecks of optimization for deep learning, however, is that the function class over which you optimize, the f of X that you are trying to minimize, has to be a very rich function class to capture all these properties of your data. F of X for deep learning today is a non-convex loss function. And that is what makes training a deep network difficult. And this is the focus of my thesis work. High-dimensional, large-scale, and non-convex optimization problems. Well, this is a very popular area to work on for the last half a decade. What do we know about this? So if you look at results in matrix factorization, these are typically motivated from things like principal component analysis or dictionary learning and matrix factorization. And they will predict that this function f of X has many, many global minima. And all these global minima are kind of equivalent to each other. So you can jump from one global minimum to another simply by an orthogonal transformation of your weights. So the picture that these techniques give you is that the loss function f of X has multiple equivalent global minima. Is this true for deep networks? We don't really know. There are similar analyses in physics, where this style is much older. You would write down the loss function f of X as a high-dimensional Gaussian process or spin glasses, so on and so forth. And these results predict that there are exponentially many critical points of the loss function, locations where the gradient goes to 0, where you would get stuck as a first-order algorithm, exponentially many of them in the dimensionality of your object. And they exist at all energy levels. So it is not as if there are many equivalent global minima, but there are all sorts of local minima spread in between where you might get stuck. Is this true for deep learning? Which one of these is true? We don't know. At the same time, results in optimization would try to accelerate the training of a deep network. So for instance, you're stuck at a saddle point where you're traveling in regions which have very low gradients in some dimensions. The ideal way, or one of the ways of accelerating your algorithm, is to add a little bit of noise so you fall off the saddle point. We don't use these kind of techniques for training deep networks today. We use plain good old-fashioned stochastic gradient descent. Let me kind of elaborate more upon the paper that I have written in bold here, which uses a spin glass model to paint a picture of the energy landscape. A spin glass is a model from statistical physics, which is very similar to an Ising model. It is built upon spins, which I denote by sigma. So sigma is a capital N such spins, and sigma I1 is a real number. The energy of a spin glass, the Hamiltonian of a spin glass, is a sum of p tuples of these spins. So you pick p indices out of n, and then you multiply them together, and you add such quantities. They're added after multiplying together by this coupling matrix, coupling scalar. So J is called a coefficient, which is the coupling between p tuples of your spins. And in a mean field spin glass, J is a Gaussian random variable. So the Hamiltonian of a spin glass is a random variable. It depends on J. And the reason this model is kind of very useful is that it is a very prototypical hard non-convex optimization problem. And we are going to understand how is it different from what we see in deep networks. How are they similar to each other? You might have seen an Ising model before. An Ising model lives on the R2 plane. So these are n spins. Each pixel is a spin here. At low temperature, for a ferromagnetic Ising model, when J is constant and equal to 1, your neighbors don't really like to be far away from you. So all neighbors like to be together in the direction that they're pointing at. Let us say the spins of +1 or -1, and you get pictures like this. So these are called long-range correlations in an Ising model. At high temperatures, these neighbors are more or less independent of each other, and you get a fairly random configuration. So this is how spin glasses look. So for us, the equivalence of this model with that of a deep network is that the spins, you should think of them as weights of a neural network. These are the places where the weight distribution is supported. It is a variational neural network model. And the coupling constant J is really all the correlations of different paths as they go from a given input pixel to the loss function. Writing down the Hamiltonian allows you to compute a lot of statistics. Statistics about how many critical points exist, where are they located, how is the topology of the loss function, so on and so forth. And I'll give you a short snippet of one of these results. Let us look at the number of critical points. Critical point is a location where the gradient goes to 0. If it is a critical point of index k, it has k negative eigenvalues. So k equal to 0 is a local minimum. It has no negative eigenvalues. The expected number of critical points is exponential in the dimensionality. So, and you can see this from this formula, which is very interesting work by a physicist from NYU. If you have n spins in your neural network, if you have n weights, there are exponentially many critical points for a spin glass. And that there itself is a interesting fact. The exponent in the exponential is this function called theta, and we are going to see how it looks now. So this one picture tells you everything about the complexity of a spin glass. And focus on the black line for now. This black line is theta for k equal to 0. When the black line is above the x-axis is the energy of the Hamiltonian. So these are the locations with the least with the lowest loss. As you go to the right, your loss increases. So the location where the black line hits the x-axis is where the number of local minima vanishes. To the left of it, there are no local minima up to an exponential order. To the right of it, there are exponentially many local minima. So there are exponentially local minima everywhere in the energy landscape. It is not as if they're concentrated towards the global minimum. They're everywhere. Moreover, look at the blue line now. So this is the line for k equal to 1. It is a saddle point with one negative eigenvalue. It starts a little bit further from the local minimum. So in this particular region, there are only local minima. There are no saddle points. As you go to the right of this point, however, you have both local minima and saddle points of index 1. In fact, as you go far to the right, there are critical points of all indices everywhere. It is a very, very, very hard optimization problem to minimize a spin glass. Fact 2. In this region, if you focus, you can get a characteristic of the topology of the loss function. And you can show that the loss function really looks like different valleys, but they are completely disjoint from each other. It is very hard to go from one valley to the other without climbing a hill. And if you are a first order algorithm, climbing a hill is exponentially hard. It takes exponentially long time. As you go higher up in the energies, it becomes a little easier to go to a different local minimum. Instead of climbing hills, you have to go through something that are called entropic corridors. So you squeeze through a corridor, to reach a local minimum. Squeezing through a corridor is also very difficult for a stochastic algorithm. And this is why like moving around in a non-convex landscape is difficult. One, you have to climb hills. Two, you have to squeeze through corridors. A spin glass, however, does not quite have the right topology. I believe that it has the right complexity, but the topology is a little off. And here's the reason why. So if you look at matrix factorization, think of writing a matrix X as a product of two matrices, A and B. I can plug in any other matrix in between A and B, and the answer doesn't change. So X doesn't change. P could be a permutation matrix. It could rotate the rows and columns of A and B. Or P could be a general matrix with an inverse. So long as you can find such a P, you can move around the parameter space. Matrix factorization has orthogonal symmetries, where P is a permutation matrix or any orthogonal matrix. It also has continuous symmetry, so I can move around local minima, global minima in this particular case. Spin glasses do not have this, just as we saw for the topology. There have been a few new results which basically use this observation to show that over-parametrized neural networks with two layers have no local minima that are not global minima. Moreover, the entire set of global minima is completely connected to each other. You can always go from one to the other. It may be very hard, but you can. There are similar models in statistical physics which also have the same flavor. So these are called XY models, where instead of being a product of individual terms, the Hamiltonian is really like a cosine of sigma I minus sigma j. So you can now imagine that if you are at this local minimum or a global minimum, you can get a switch together the spins to create a critical point of this shape. It is not an isolated critical point anymore. It has a large volume. In fact, it spans the entire domain. And these models are statistical, so they're much more general than, let's say, two-layer neural network, and they have the same qualitative flavor that we are trying to analyze these days. There's also results in planted spin glasses, which are very relevant to deep learning. So around 2016, I, however, changed tactics. So instead of trying to come up with a good model for a deep network, how about we try to understand what optimization is doing to a deep network? This picture was kind of what started this realization. If you see most neural networks today, and this is a picture of state-of-the-art neural networks that have done well on ImageNet over the past few years, every single network on this plot was trained with one algorithm, and that is stochastic gradient descent. It is a very, very simple algorithm. At each iteration, it takes a step in the direction of the negative gradient, and it keeps doing that forever. It is an approximate step. And yet it works so well for training state-of-the-art deep networks. So here is like a very, very stark paradox. If the loss function of a deep network is so hard, then why does a simple algorithm like SGD work so well for it? And let us see one experiment which elaborates this result. So I trained a convolutional neural network, and I'm evaluating the Hessian of this neural network after it has finished training. And what I'm plotting here is the eigenspectrum of the Hessian, a histogram of the eigenvalues of this matrix, which measures the curvature of your loss function. What you'll immediately see is that there is such a large proportion of eigenvalues that are basically zero. About 95% eigenvalues out of, let's say, 1,000,000 dimensions are basically zero. There are a few positive eigenvalues, which are directions of increasing curvature. And there are also a few negative eigenvalues, which are directions in which the loss decreases that your optimization algorithm hasn't found. In fact, this location that SGD has found is not a local minimum. It is a saddle point. There's both positive and negative eigenvalues. The key point about this picture, however, is that it remains constant irrespective of the network that you're training, irrespective of the data set that you're using. It is an artifact of over-parametrization and correlations in your data. Stochastic gradient descent by the end of training converges to regions that are very wide. They have lots of zero eigenvalues. And now you can ask a very simple question, right? So I know that SGD works well. I know that it finds these wide regions by the end of training. So I'm going to go looking for these regions explicitly. I might be faster while doing so. And here's a simple trick that you can play on the loss function to do so. So I took the original problem, which is x star equals argmin of f of x, and I'm going to rewrite that as argmax of e to the negative f. And you haven't done anything yet. You've simply taken the problem, exponentiated it, and made it even worse than what it already was. You're not going to smooth this modified loss function with a Gaussian kernel. So G sub gamma is a Gaussian of variance gamma. What such a smoothing does is that it destroys all regions in the parameter space which have high curvature, and what you're left with is these wide regions. It makes these wide regions easier to find. We'll call this function local entropy, and you can minimize local entropy using techniques from Markov's and Monte Carlo. And it works really well. You're finding these regions explicitly, so you descend faster. You can show that the loss function is smoother. You can also get generalization bounds using uniform stability. But the key point is that not only do you descend faster, you also get improved generalization error in some cases. But it does look like a hack, right? So we just like exponentiated the loss function, smoothed it out, and now magically you get better answers. Let us look at some results in statistical physics which tell you why it might be working. So this is a cartoon picture that I've drawn from analytical results on this model called a binary perceptron. A perceptron is a one-layer neural network where the weights of this object are +1 or -1. There is a discrete combinatorial optimization problem. Every single point in this circle is one binary perceptron. The red points and the blue cluster of solutions are all perceptrons which obtain 0 error on the training set. You can show using these results that the solutions in this blue cluster are the ones that also generalize to new data. You can do this computational analytical in physics using replica theory. So you want to find the blue regions if you are doing machine learning. But you'll immediately notice that there are so many red dots and there is one blue cluster. There are exponentially many sharp minima for a perceptron or local or global minima that are isolated solutions, whereas there is a constant number of such blue clusters. Finding them is extremely, extremely hard. If you're a greedy and local algorithm, you're always going to find one of these solutions instead of finding this one wherever you start, because there are just so many of them. What local entropy does is that it removes these red points, it diminishes them, and then finding the blue regions becomes easier. So it amplifies this large deviations phenomenon by this special smoothing term. In fact, it is extremely remarkable that SGD finds the blue region without even trying. And we'll kind of solve this towards the end of the talk. Local entropy at the end of the day was a smoothing of the loss function, right? So now you would ask me, what is the best way to smooth a loss function? Maybe we can use partial differential equations. Here's the heat equation. The heat equation is a PD in two variables, x and a parameter gamma that you should think of as time. At time equal to 0, u of x equals f of x, which is the original loss function. U sub gamma, which is the derivative with respect to time, equals the Laplacian of u, which is the trace of the Hessian of u. So the heat equation is called the diffusion equation. It governs the flow of heat in this room, and it starts with its initial conditions and then smooths these initial conditions. What you can show is that local entropy is the solution of a slightly different PD, the Hamilton-Jacobi partial differential equation. In addition to using the Laplacian for smoothing, it also has a term which is negative grad u squared. It uses gradient information to smooth. It smooths faster where the gradient is larger, and that is why it is better than the heat equation. This PD has very nice connections to stochastic optimal control. And let me kind of write down a system to analyze this further. The dynamics for our weights is as follows. So dx is the incremental weight update per iteration. It equals the full gradient on your data set. This is not the stochastic gradient, it's a gradient on the full data set, corrupted by some Brownian motion, which is really a stochasticity of stochastic gradient. Instead of doing gradient in the steepest descent direction, however, we are going to allow ourselves a little bit of control. So alpha is a control that you're allowed to pick to modify the direction of descent away from the steepest descent direction. How would you pick alpha? Well, look at all trajectories of your stochastic differential equation. And after some terminal time t, you would like these trajectories to be as deep into the energy landscape as possible. So you have to minimize f of x at capital T. And I like trajectories out of these which let me use as little control as possible. I don't want to modify the steepest descent direction too much. So this is the integral of alpha squared along this trajectory. This is a well-defined stochastic optimal control problem. The expectation here is taken over Brownian motion. And the best control that you can pick is not surprisingly the gradient of the value function. In this particular case, the Hamilton-Jacobi-Bellman equation. So this is called a controlled stochastic gradient descent because you're allowing yourself a little more control on top of HGD, and it is very, very close to local entropy. This shows that local entropy is not a greedy or a local algorithm. It is a non-greedy and a non-local algorithm, and that is why it is better than HGD. Now that you've opened kind of the door into PDs, you can look at new PDs for deep learning. So here's a simple trick. You take your Hamilton-Jacobi equation and set the Laplacian to 0. Now you are doing smoothing only on the basis of your gradient information. This is a simpler object. It is also older. And you can actually plot the entire solution in this particular case. So this is a one-dimension example. And f of x is given in black here. So it is, let us say, generic non-convex optimization function. Local entropy is plotted in red. You see that it smooths the energy landscape and lifts it up a little bit. The non-viscous Hamilton-Jacobi equation, where the Laplacian is 0, is actually a very interesting loss function. So it hugs the local minima of your old function. It has these sharp regions where you had local maxima in your original function. And it is decidedly a little worse than local entropy. But it's still kind of good enough because it gives us a very nice connection to proximal point iteration. Proximal point iteration is a very old algorithm in optimization, all the way from like 55 and 65, depending on how you look at it. The minimizing the non-viscous Hamilton-Jacobi equation is equivalent to doing proximal point iteration. If you are at a location xk, your next iterate, xk plus 1, is always going to be better than xk because you're doing an explicit minimization in your neighborhood. The parameter gamma, which was time for the PD, which was this bandwidth of smoothing for the Gaussian, is also the step size of proximal point iteration. Proximal algorithms are very stable with respect to step sizes, and this is why they are nice for doing deep learning. You don't have to worry about the value of gamma too much. You do these, you execute this set of updates stochastically inexact though they may be, and it works.
You might have said it's also the gradient of u of xt and xk.
Yes.
That function.
Yeah.
That's a nice thing to say.
Yeah.
Which means the function is more convex. You showed it on the graph. It means you're minimizing a function which is much more convex than the original function.
Yes. Let us look at how one would go about exploiting these ideas that connect kind of statistical physics with regularization as coming from a PT. And I'll show you an example of distributed training. Distributed training of deep networks is a kind of a very hard problem today. So imagine you're Google and you have a large cluster sitting in your backyard. But because deep networks are very, very big objects, it is very hard to communicate across different computers. They are just too big. If you use a very large batch size while training your deep network, things don't work so well. You don't get good generalization. And now we know the reason for this. We didn't know it back then. And this tussle between generalization and communication is at the root of all approaches to distributed training today. Here is an algorithm which tries to solve this. It is called elastic SGD. It trains n neural networks in parallel. So f of xk is the kth neural network out of this n, but it does not train them independently. It couples the weights of these neural networks using a proximal term. This has to be proximal. It can be quadratic, L1, it doesn't matter so much. But the idea is that if all your friends are in nice regions of the parameter space, they are going to pull you out if you're in a bad region. And together, all these replicas find good regions of the parameter space. In fact, this is running for on your Android phones right now for keyboard prediction. Every night when you plug in your phone for charging, your internal model of the phone is merged together with the models of your friends, and tomorrow morning you get better predictions. So it works at the scale of Google under a federated learning set. You can show that elastic SGD works because it minimizes local entropy. All this completely distributed algorithm across different computers is equivalent to minimizing local entropy using a sequential Markov's and Monte Carlo algorithm. You can build upon this insight and create another algorithm which is called Parlay. So Parlay is an algorithm which executes elastic SGD across multiple computers, and on each computer it actually executes entropy-sgd, which minimizes local entropy using an MCMC algorithm. So by coupling together these distributed and sequential updates, you get even better performance than either of them together. So this is pretty close to the state-of-the-art neural network back then on CIFAR. The black curve is the validation error of stochastic gradient descent. And you will see that even after the first epoch, Parlay is so much better than SGD. You're not only training faster, you're also getting much better validation errors. Because you have all your friends helping you, you don't have to look at the entire data set also. So each of these replicas can work with disjointed subsets of your data set. They are pulling you towards regions that are good for their examples. Consequently, you do well on their examples also, while taking gradient steps on the examples on your computer. And then you get a trivial speed up, right? Because you're just working with less data locally. Formally, it looks like this. So entropy-sgd is a system of two stochastic differential equations. X are the weights that are being updated. Y is kind of a dummy variable which creates, which is used to estimate the gradient of local entropy. Elastic SGD, on the other hand, is again a system of two differential equations. And you will recognize this term yk minus y bar, which is how far you are away, you are from all your from the average of all your friends. Turns out these two systems of equations are equivalent to the same homogenized dynamics in the limit that epsilon goes to 0. In the limit that you're doing infinitely many Markov-Chain Monte Carlo updates, or you have infinitely many replicas, these two things are exactly the same. So we kind of identified some properties about SGD, the fact that it converges to wide regions. We came up with algorithms that build upon these properties, amplify these properties to obtain good empirical performance. But the fact remains that SGD itself works well, right? It is a very, very simple algorithm. So what is so special about SGD that makes it work well? Let me give you a short view of generalization theory. So if you look at results in statistical learning theory, they would predict that in order to do well on new data, you need to regularize your loss function. You need to restrict the class of functions that f of x belongs to. And now think with me, right? So stochastic gradient descent is an optimization algorithm. It is not allowed to change the loss function that it minimizes. I give you a function, you minimize it to the best of your abilities, and that is end of business amongst us. If you look at results in Bayesian theory or information theory, it would predict that I need to regularize the posterior density of my models. If my weights in the neural network do not retain too much information about the training data set, they are robust to new data. And that is how you would get generalization. We don't use these kind of penalties for training deep networks today. In fact, when you try to use them, they don't work that well. They don't work as well as SGD. What you can prove is that SGD itself performs variation inference. And this is kind of a very bold and stark statement. So I have an optimization algorithm. It is implicitly performing variation inference, which is something to do with models. It is something to do with regularization. And here's how you would go about parsing this result. We are going to look at not one trajectory of SGD. If you're looking at one trajectory of SGD in a non-convex landscape, you're doomed to fall into the first value that you encounter, and then you cannot make any more statements about this algorithm. We are going to look at the entire steady state distribution, which happens at time equal to infinity. And I would like to simply characterize this steady state distribution and see how it looks. I will call this rho SS. Rho SS is the solution of a variation optimization problem that can be written as follows. So focus on the second term here. It is the entropy of your argument rho. Rho is the variable of optimization. Stochastic gradient descent likes its posterior densities to be as entropic as possible, as spread out as possible into parameter space. This is the implicit regularization of SGD that you will see being talked about in the literature. It is what is also called as the information bottleneck principle, which comes about as a way of creating representations that are robust to new data. Turns out SGD has information bottleneck built inside it. If you look at the first term, it is the average of your of a loss function called phi with respect to your distribution rho. All this while we are talking about a loss function f of x. Turns out f of x does not even show up in this formula. Behind your back, SGD is minimizing a loss function phi instead of minimizing the loss function that you gave it. It is taking gradient steps on f of x, but still ends up minimizing this function phi. And in fact, you can show that for deep networks, phi and f are very, very different from each other. The critical points are different, are quite different. So SGD may reach the critical points of phi and not f of x. Formally, it looks as follows. So every stochastic differential equation has an associated Fokker-Planck equation, which gives you the evolution of the steady state density. So this is a partial differential equation. The solution of this partial differential equation is the final steady state density of this Markov process that happens at time equal to infinity. Turns out the solutions, the steady state distribution can be seen as a solution of a variation optimization problem, and that has a very nice structure. So it is the K divergence between the current state rho with the steady state distribution. So it is kind of like the difference between rho and your final solution. And you would imagine that, let us try to imagine this result in deterministic convex optimization. So you are at location X, you're trying to go to a location X star, and this formula really says that I'm minimizing X minus X star. And that's kind of obvious, right? So if you are any algorithm worth its salt, you would be minimizing X minus X star. What is fantastic, however, is that you're minimizing it monotonically. Trajectories of the Fokker-Planck equation perform steepest descent in the Wasserstein metric on the variation loss function. Phi that we saw is simply log density of the steady state distribution. I mean, it's kind of a very stark result, right? So I end up minimizing a function that is different than the one that I set out to.
Can you go back one slide? So you're looking at, so the right-hand side goes to 0.
Yes.
Of the equation in the middle.
Yeah.
And somehow grad f has disappeared.
Yes. So phi is a function that is defined implicitly in this particular formula. It is defined as using the solution itself, right?
But it definitely involves f.
Yes. So you can show that phi depends only on f and d. In particular, it does not depend on beta inverse, which is the step size and the batch size and all these kind of things.
Yeah.
So it is a function that exists in the problem to begin with.
This is JKO.
Yes, so JKO, this is exactly equivalent to JKO if D is identity. So this is like JKO plus some non-steepest descent direction
But
gradient.
f is certainly a problem.
It would be a problem.
Well, you can get rid of f from there.
I mean, let us see why current literature has missed such an important fact. And I'm going to show you a small observation which hints at what is going on. So if I show you these two images, a white cat versus a white dog, they are not that different to your eyes. Most of the pixels is basically white fur, and consequently, the gradient that a deep network sees on these two images is also very correlated to each other. The stochasticity of stochastic gradient descent, which measures the correlation in your gradients across the images in your data set, also happens in a very, very small subspace of the total subspace of your neural network. So if you train a network with 10 million parameters, the stochasticity happens in a subspace that is as small as 0.5%. The rest of it is simply gradient descent dynamics, not stochastic. And as soon as you have this mismatch between the stochasticity and the gradient descent dynamics, you get a result like this. Phi becomes different than f. If instead of being 0.5%, it was 100%. If the correlations were constant for all your weights, then you wouldn't have this result. But because we are dealing with real data, because we are dealing with over-parametrized loss functions, we have this result. In fact, you can kind of ask yourself, what kind of solutions does SGD give me? You would imagine that SGD is a bouncy ball, and it kind of goes into a local minimum and then bounces there forever. Exponentially long times, it climbs up hills. But you can instead show that trajectories of stochastic gradient descent look like closed loops in the parameter space. And you're allowed to travel forever on these closed loops. These are exactly the critical points of the loss function phi that we've been talking about. The critical, and they in general are not the critical points of f of x. You can also see this in experiments. So this is an experiment where I took a very, very long trajectory of stochastic gradient descent, 100,000 epochs long, and I'm computing the fast Fourier transform of the derivative of this trajectory. If this trajectory were really Brown in motion, then this would be the FFT of white noise, and it should be flattish. What you instead see is the distinct presence of low frequency modes. These are the periodic modes in this trajectory. These are the limit cycles that you see. It is not as if this trajectory is near a local minimum. As you train a deep network, the gradient of this network barely goes to 0. If you started out with a gradient of, let us say, 0.03, the magnitude of the gradient, it falls down by not much more than a factor of 3 across 100,000 epochs. So you're traveling in regions of the parameter space which have very high gradients, but doing it forever. This is a 2D example which kind of shows you how these limit cycles might look. So I created a 2D loss function. The two red dots are local minima of this loss function, and there is a saddle point at the origin which connects them. These black lines are the critical points of phi. These are the limit cycles that SGD will get into. In optimization, we spend a lot of effort trying to show that a gradient descent does not converge to saddle points, or stochastic gradient descent escapes saddle points quickly. But for real data, for over-parametrized architectures, SGD is perfectly happy not to converge to saddle points, but around saddle points. So this is a fundamentally different result than what you would get from optimization techniques. Here's how it looks formally. So I'm going to again look at a stochastic differential equation, which is a model for stochastic gradient descent. And it is turns out that it's equivalent to another stochastic differential equation you obtained using another calculus. And this term here really gives you the difference between the critical points of your original loss function gradient f and critical points of your new loss function phi. This term is actually linear in the step size and inversely proportional to the batch size. So in practice, when you're training with high learning rates or small batch sizes, you're very far away from the critical points of your loss function. One thing that I find endlessly fascinating about deep learning is that the model class over which you're optimizing, the loss that you impose on your images, let us say regularization or pre-processing, and the generalization performance are completely tied together. This is not so for SVM. So in SVMs, we only worry about picking a kernel, and then everything else is done by scikit-learn. The power of deep networks, I believe, is really coming from this entanglement together. And understanding how these affect each other is what one would like to do in order to build an understanding of deep learning. How are we going to do it? Well, if you are a learning theorist, the first thing you do is you take your data set and throw it out of the window in your analysis. It is very ironic that machine learning does not understand the data that it works on. It only understands models, it only understands optimization. Properties about real data and the isotropicness of the gradients, the correlations of your gradients, is one such property of your data set, is what we need to kind of put into the analysis in order to understand these processes better. I would like to conclude here, but before concluding, I would like to acknowledge my wonderful co-authors. These have been more than co-authors in some cases, so mentors, well-wishers, friends, and they have been with me for many years now. So physicists, machine learning people, let's see. So mathematicians, Stan is here, roboticists from my master's work, then Carl from Autonomy. And I would also like to thank my committee who have tolerated these talks, longest talks for 2 years now. But I think finally, I would like to thank my advisor. So it is, I've been very lucky to have an advisor like Stefano, and I don't think I can put in words as to how much I have learned from him. So he said in the beginning that he learned from me. It is debatable who learned more. In 25 years, I would like to be like him, and I think that is the that is what I would like to say about him.
Talk to my doctor.
I mean, he thinks of himself as the ringmaster, so he has everyone around him. These are the people I have been hanging out with in the lab over the years. Some of them have graduated, some of them are still here, but a very fun bunch that I've come to like and respect and love. Well, maybe not all. I would also like to thank my family, and this is to them is what I've dedicated my thesis to. So parents always have a very naive optimism in your abilities. It has helped me more than they know. About future whereabouts, in my immediate future, I will be here. For those of you who don't know this place, this is in front of Powell Library. You should go there and take a look if you haven't yet. In the long-term future, I will be joining the faculty at the University of Pennsylvania in the electrical engineering department. And this is where I will be. You see that the trees have no leaves, so it is decidedly a worse place. And I will miss UCLA and the grass more.
It has trees, has leaves. Like right there. Don't say anything.
Yeah, so Fee has very fond memories of Penn, and I hope to create them also in the coming years. Thank you for your attention. I will take questions if you have.
It's precisely 35 minutes. 36. So we'll take a few questions from the general audience before we kick everybody out. And so any questions or comments?
Oh, yeah, maybe regarding one of the last topics that you mentioned about connecting with real data sets. I wonder if you can say a few words about that.
Yes, so my basic intuition is when we talk about building principles for deep learning or creating a theory of deep learning, what kind of theory would you like to create? So new architectures come out every day, new data sets are going to be generated every day. We would like principles that remain true across them. But, and it's kind of very hard to say that I'm going to write down a formula for what a deep network looks like and then analyze this formula. Instead, I kind of take motivation from how thermodynamics was created in the earlier part of the 20th century, where you're kind of trying to find quantities like enthalpy, entropy. People were fighting about how to even plot them against each other back then. The matrix of correlations of your gradients D is one such property. So the entire thing that we said about stochastic and descent, limit cycles, new loss functions, so on and so forth, is all coming from understanding the properties of one matrix, which you can write down, compute. And so long as you know your new data set has these properties, all this theory remains true. You need to find kind of more such quantities. So you could be mutual information in your weights with respect to training data, or cross correlation of your weights after being trained. But these are the quantities which you can just like sit down and evaluate and then build your theory on top of it.
You misunderstood your question, but did it answer your question?
Oh, more or less, yeah. So the idea of relating the data to your system.
Yes, so we don't have models for data, and that is where the buck stops.
Right.
But we can sure evaluate things, right?
I understood your slide as saying, a theory that connects learning and the optimization part. This could be related to a particular data set, which is part of the contemporary discussion, the organization question.
Yes. So optimization has always been completely blind to generalization. Machine learning has always been completely blind to optimization. So you would like to minimize the pack-based bound, but you have no idea how to go about doing it. And magically, somehow, we see simple algorithms like SGD straddling this fight.
No question. Okay. So then we'll ask you guys to step aside so we can build practice.
Bye bye, everyone.
Was a great talk.
Thank